Good evening, everyone. Welcome to the week 4 live interaction session. Let's just wait for a few minutes for others to join before we begin our session for today. So let me just present my screens. I hope I'm audible. Is my presentation visible? Anybody can confirm?
Yes.
Okay. So Welcome to the week 4 live interaction session for the course Polymers, Concepts, Properties, Uses and Sustainability. This course is offered by Professor Abhijit Deshpande sir from the Department of Chemical Engineering IIT Madras under the NPTEL program. Myself Pratyumnan, a research scholar at the Department of Chemical Engineering IIT Guwahati, Assam. I conduct the live interaction session for this course where we meet and discuss about the concepts and the concepts related to the course and solve some of the problems. So we have come across almost 3 weeks and today we are in the fourth week. We have completed the fourth week of the course. So till now we have learnt about what is polymers, their the overview of the concept, their properties, uses and sustainability aspects. So in the last session we went on discussing about the properties of the polymers more in detail. So I hope everybody here are able to recollect that we discussed about the different states of the polymer, the crystalline and the amorphous state and the semi-crystalline nature of the polymer, and we also discussed why 100% crystallinity cannot be achieved in the polymer, and we discussed about the kinetics of crystallization, where we discussed about how to obtain crystals from the polymer melt and what and how the cooling rate and then the temperature of cooling these polymer melt affect the type of crystals that is formed. We discussed about the types of crystals that can come out of these macromolecules. We also discussed on how to prevent the nucleation in these macromolecules, what are the kind of techniques or manipulation that we can do in the synthesis condition so that the polymers will never crystallize. It will be totally in amorphous state even if we cool down. And after which we discussed about um, after that we actually went about discussing of the interactions in the polymer systems. So what are the different types of interactions, the intermolecular interactions as well as the intramolecular interactions between the polymer chains. So based on that we also solved a few problems related to this Mark-Houwink equation, and some more problems related to finding out the density of the sample. And yeah, so apart from that we also discussed about, if given a polymer to us, how to differentiate whether that particular polymer is crystalline or amorphous. So as we also saw in the last discussion that there are so many polymers that are available. We at the instant of time, if we are able to remember about 20 to 30 polymer names itself is a big deal. So it is often very difficult for us to remember about all the polymers including their properties, both physical as well as chemical. So given a situation where we are supposed to compare, we need to have some sort of a thumb rule or some sort of hints with us to determine whether a particular polymer is crystalline or amorphous in this case, or in general how the trend will vary. So we discussed about three things. If the polymers have bulky groups, then due to the steric hindrance that comes from these bulky groups, folding will not be possible. So since folding is difficult in these case, polymers of this kind with a bulky side groups usually are amorphous in nature. Then cross-linking. So because of the intense cross-linking between these polymer chain, again the interlocking makes the structure more rigid, and due to which that folding becomes in folding becomes something somewhat not feasible. So due to that the polymer chain remains amorphous in nature, and if you have something like a copolymer or blend, then even in those cases it is not possible for the polymers to crystallize. So it is predominantly more amorphous with very minor quantity of crystalline regions within the bulk sample that you take. So in this class, we are going to continue our discussion and see more on the properties of the polymer. And in fact, we are going to discuss today on one of the most important properties of the polymer, that is the glass transition temperature. So as we discussed in the last class also, using one of the multi-choice question about what is glass transition temperature, we discussed that the definition of glass transition temperature goes as that it is defined as the temperature at which the polymers undergoes a transition from the glassy state to rubbery state. So they and the glass transition is basically a transition where the polymer starts to exhibit more of a flow like behavior. So that's what we characterize it as glass transition temperature. So today we will discuss more regarding this glass transition. So speaking of the glass transition, we here discussed about the amorphous state of the polymer as well as that of the crystalline state. So amorphous state has two kind of, what do you say, amorphous polymers usually have two states, glassy state and rubbery state. So our discussion will more revolve on how does these properties or how does this nature of the polymer is going to vary below Tg, that is your glass transition temperature, and above Tg. So this is what is going to be our discussion right now. So as you know, amorphous state, so what are the characteristics of or like if you have crystalline material and amorphous material, what is the difference between these two in terms of their arrangement of the unit cells? Anyone? Difference between amorphous and crystalline materials? Yes. So amorphous materials typically don't have a specific long range order and they lack periodic arrangement. That is not the case in the crystalline materials. Crystalline material, the unit cells which forms the building block for the crystals have a long range order, and more than that there is a periodic arrangement of the unit cell. So this is the basic difference between the amorphous and crystalline, and this holds true for all the classes of the materials. So amorphous state of these polymers typically have some sort of the relaxation process. So relaxation is nothing but it is basically um, you can say relaxation is where the molecular chains of the polymer, or basically the segments of the polymers, tend to undergo some sort of an arrangement or a rearrangement in order to in as a response for that of the external environment. So the molecules that you have, the macromolecules, they tend to undergo some sort of rearrangement, and this rearrangement of the segment or the overall macromolecule is called as the relaxation. So these relaxation, since these molecules are undergoing some sort of a rearrangement, the relaxation process typically results in the generation of free volume. So any idea on what is the free volume? Like what do you, any guesses on what could be this free volume be? Yes, anyone? Because this free volume before and after glass transition temperature is going to be different, like how the relaxation is. So relaxation, if you see below Tg, what is the case is these amorphous polymers typically exhibit glassy state. So since they exhibit glassy state, the relaxation process is going to be a bit slower, or is going to be slower compared to the relaxation process that is happening in amorphous polymer in the rubbery state. And the difference between these two processes basic differs by a order of magnitude. Whereas in case if you see for, if you compare this amorphous glassy state polymer with the crystalline polymer, the amorphous process in this the relaxation process in the amorphous glassy state will be higher. So the free volume also is typically the same. It is going to be more when it is going to be more above Tg, and it's going to be less below Tg. So what is this free volume? I mean, any idea on what actually is this free volume is? Because they say that the molecules undergo rearrangement, and this rearrangement results in the free volume. Is anyone free volume? Hmm. Hmm. Well, something very close you can actually say, since they cannot occupy the same site, so there will be a space between these two segments, right? So that space, that empty space between these two, polymer, or basically the segments of the polymer, is called as the free volume. So, so the free volume will be more when you have this, I mean, post Tg or above Tg, and the free volume will be less in case of temperatures lower than this Tg. And one more thing about this polymer which is present in the amorphous glassy state is, it is actually a non-equilibrated state. If you see polymers which are going to be in the amorphous rubbery state, they are equilibrium, they are in equilibrium with the surroundings. But in case of the amorphous glassy state, they are going to be in non-equilibrium. The typical reason why this is happening is because when you take polymer melt, and once you are trying to cool the polymers, so what happens is the molecular, so once you try to cool the polymers, the thermal energy that these polymer chains have is going to get reduced, due to which the molecular arrangements are going to get restricted. And the polymer chain, so as when I say molecular arrangements are going to get restricted, which means that molecular chain mobility is also going to be restricted. So the polymers are typically more of in a locked or a arrested state, so they cannot um, change their properties when subjected to different external conditions. Like they cannot respond to these external condition or come in equilibrium. Suppose if I have a polymer melt, and let's say I'm going to freeze it, so due to this freezing state they are going to go into an arrested state or an interlock state. And if suppose I vary the temperature of the surroundings, then these frozen state polymers cannot typically um, change their uh, property according to the surroundings. Due to this, they are said to be in a non equilibrated state. So the thing is, this equilibrium, whatever is happening, should be achieved within a considerable amount of time, because some things may reach equilibrium provided if you leave them for very very long time. But so those kind of systems also exist. So here also it may be possible, but since this process, or since the system does not come into equilibrium, we say that the polymers, the amorphous polymer in the frozen state, are usually in non-equilibrated condition. So this is something typical to understand, because it is important, because for non-equilibrated state, the equation of the state, like um, these amorphous polymers do not, you can say, do not obey the equation of state, that is the function of pvt equal to 0 does not hold true for them. So because of this, what happens is, since the polymers are in non-equilibrated state, the way they cool you, the way you cool down these polymers will have a effect over their properties. So the properties of the polymers from here onwards will depend upon the history. So the way how you cool will make things different here. So if you, basically if you take same polymer melt and take, let's say, 50 percentage of each of them, and then if you try to cool these polymers through different conditions, different cooling conditions, might be in terms of temperature or cooling rate, then the final properties of the polymer will not be the same, even though they come from a similar polymer melt parent. Their properties will change after being frozen, because of this, because they are not in the equilibrated state condition. So as we discussed that so can anyone tell, I just said that the free volume is nothing but it's basically the empty spaces between the segments of the polymer chain. So I told that as the temperature is higher than the glass transition temperature, the free volume will be more. If the temperature is lower than the glass transition temperature, the free volume is going to be less. Any explanation on why so? Mm. Mm. Okay, and in case of above TG? Mm. Yeah, yeah, yeah. So what kind of energy are we talking about here? Is it um, thermal energy? Yeah, yeah, that's fine. So as rightly said by one, in the who's so below TG, what happens is, since majority of the polymer is going to be in the glassy state, so the chains will be very closely packed. They will, the thermal energy will not be sufficient for them to move around. Since the temperature is less than TG, the thermal energy will be less for the chains to be mobile or to basically go some sort of a rearrangement. So that is typically the reason why the free volume will be less in at temperatures less than TD. But once you basically increase the temperature above Tg, the the thermal energy increased thermal energy is available for these polymer chains. So due to the increased thermal energy, the polymer chains can rearrange themselves or can undergo some sort of a molecular arrangement, which basically results in more free volume for the system. Yeah, yeah, go ahead. Mm. Mm. Ha ha. Mm. Ha. Yeah, the arrested state will not be in equilibrium with the external surroundings. Mm. Mm. So the thing is probably that the density will not be same for, let's say for example, you take one polymer melt and you take same polymer but different I mean same polymer melt, like two polymer melts of the same polymer, and then let's say as you said it is at 30 and then you are cooling it down, but the rate at which you cool, let's say for 30 to 16, if you are cooling at let's say 1 degree Celsius per minute, and let's say in another case also you are going to bring down to 16 degrees Celsius, but let's say you do that much faster, let's say at 3 degrees Celsius per minute. So what happens is both these polymers, when you obtain, their physical properties like volume and density will not be the same. Hmm. And let's say if you are after that also, if you are, let's say you are increasing the temperature or something, then they will not try to, what do you say, come in equilibrium with the external condition. So let's say you have this two systems, and then if you try to adjust after that any temperature, let's say from 16, if you are going to take it back to 20 or 25, let's say any changes whatever you do, this will not this will not try to, come in equilibrium with the surroundings. It will be like it will take a long time for it to balance with the external surrounding. So uh, so I hope I can continue, right? So similar to this free volume is what is the relaxation process as well. So if your relaxation process is instantaneous, what happens is the molecular arrangement is going to happen fast. So since this molecular arrangement is going to happen fast, more amount of this energy is going to be dissipated in making sure that this molecules gets rearranged. So due to this, if the relaxation is very fast, we call this as a system of we call this system as perfect energy dissipation. If the relaxation is very slow, then what it actually means is the amount of thermal energy that this system possesses, what it is actually going to dissipate for this molecular rearrangement is going to be less. That is the reason this relaxation process is very slow. So because of this, you can say that since the amount of energy that is being lost, or basically you can say the amount of energy expended for this molecular arrangement is less, so you can say that majority, as the energy needs to be conserved, so majority of the energy will be stored within the system itself. So this is, so if the relaxation process is fast, then the polymer system will be more of a perfect energy storage system. So here the time scale is of an importance of whether the process is going to be fast or slow, and with this we also basically go for a cooperative scale. So I hope everybody here can remember what was taught in the course, the WLF equation. Any idea on WLF? I mean, what is the full form? Why do we use that? So WLF is William Landau Ferry equation. So it's basically something that is used to describe the time temperature superposition of these polymers. So we will discuss more about that. But before that, we will see how to calculate the free volume of the system. Just a second. No, no, I have not moved the slides yet. It's just as okay. So can I say that the overall macromolecular volume is nothing but it is the sum of the molecular volume plus free volume. I mean, I hope there is not much confusion regarding this relation. It makes sense, right? So when you take a particular system, let's not talk about polymers. Let's say a typical system. Let's say a cube. So that cube, let think that it has some material stuffed inside that cube, and apart from that, whatever the space is there, that is going to be empty. So the overall volume of that cube will be nothing but the volume that the material has occupied plus the empty space whatever is there. So since those are the two components, it's just the equating the, I mean, it's just that the volume of the cube is going to be the sum of the two. Similarly here also, in case of the macromolecule, over the entire overall macromolecular volume of that system is nothing but it's going to be the molecular volume that is basically occupied by your polymers and the segments of the polymers, the macromolecule and the monomers. I mean, the monomers connect to form the segments which then connect to form the macromolecule. Apart from that, you also have the free volume. So I hope there won't be any much doubt with that. So this macromolecule, since it's a function of time, it can be described as, it can be described using this relation. So this is the fraction of, or you can say VF, that is your free volume divided by the total volume of the macro, or the, you can say overall macro molecular volume. So this is nothing but this is equal to Fg plus alpha times T minus Tg. So yeah, Fg is nothing but it's going to be the free volume, or you can say the free volume fraction at the glass transition temperature, and the extra factor is usually given by this term. So it's again simple. So you have to basically calculate your free volume, let's say at a particular temperature. So you know what will be the free volume fraction at a at your glass transition temperature. So that one plus that extra factor that you need to take into consideration so that you can get the value of the free volume fraction at the temperature that you wanted to. So this is one. So here, so as we discussed that before, right? So how did we say that this is a way to actually be very clear about what I told. At temperature greater than Tg, the free volume is going to be more. So you can say here, so since T is greater than Tg, then it means that this component is going to be positive. So Fg is also a positive quantity, volume cannot be negative. So two positive quantity, if it is added, it will be more. Suppose if the T is less than Tg, then this will be negative. So Fg minus of some value. So that means the free volume is going to decrease at a temperature T less than Tg. Ft increased, and at T less than Tg, Ft decrease. So previously we explained this qualitatively. Here, using this equation, we can see this more as a, quantitatively. How does the T and the Tg, I mean, how does the free volume and the T varies varies. So that's the thing. Then how many of you remember the viscosity equation that was given? Uh, so I so that viscosity of the polymer can be given some way by like this. The viscosity is given by this equation. Eta equals to exponential a, sorry, it is b by a times vf. B and a are empirical constants. V by Bf. So V is your overall macromolecular volume and Bf is nothing but your free volume. Now you know that as T increases, I mean T greater than Tg, your Vf is increasing, right? Vf is increasing. Okay, let us keep this way. So if T is greater than Tg and T is less than Tg, how does this viscosity equation going to change? Like what will, based on the temperature, what will be the changes in the viscosity? Or you can say, tell me the viscosity dependence on temperature using this equation. You know that as T is greater than Tg, F, the free volume has increased. So use that and then tell me how the viscosity will change depending upon the temperature. There is also another way to quantitatively see few things which we described qualitatively in the last half an hour or so. So you know how your free volume will vary with the temperature. Once you know the free volume variation with temperature, you need to use that to get how does the viscosity will vary with the temperature. Keep B and A as constant as I said previously. Just see viscosity as a function of, as an exponential function of V by Vf. So I hope this will be clear. As T is greater than Tg, we saw that free volume fraction increased. So free volume fraction is nothing but Vf by V. So Vf by V actually increased. So the Vf by V is increased. So it will be here that it is the expression relates viscosity as an exponential function of V by Vf. So let me put it this way. Is this fine? So if this is the case, if V by Vf is going to decrease and let's say B and A are constant and then that is not going to affect, then exponential of certain term which is decreasing. So it's a decreasing function. I mean, uh, let us not take it that way. So exponential of a certain quantity which is decreasing. So that means a quantity is decreasing, so exponential of that quantity will also decrease. So which means eta decreases. That means your viscosity is decreases. Is this fine? V by Vf decreases. So exponential of a term which is decreasing will decrease, so eta will decrease. Okay. So similarly here I write it this way. So f of t increases, so which mean, sorry, f of t decreases, so which means v by vf is going to increase. So as v by as a exponential of a increasing value will increase, so eta increases, so which means viscosity is increasing. So what does this mean? T is greater than Tg, eta decreases, and T is less than Tg, eta increases. So what actually happens in this at this glass transition temperature point? So as you so can I say that at Tg the viscosity is decreasing. So as I go from low temperature to Tg, then to high temperature, viscosity is decreasing. So the polymer is going to exhibit more like a flow like behavior. The ability to flow will be more as we increase the temperature beyond Tg, and similarly if I cool down, uh, then the viscosity is going to be increasing, so which means it's going to exhibit more of from melt to rubbery to glassy state. So does this go according to the definition of how we define glass transition temperature as a transition between the glassy state to rubbery state, or basically a point where the polymer tends to exhibit flow like behavior? Or somebody rightly said in the last class, from elastic state to viscous state. I mean, from a more of an elastic state to a more of a viscous state. So, so that was a qualitative definition, and I hope using this equation we try to also see that a bit more quantitatively without numbers, obviously. So that was about here. Then after this, let's see few of the things or these things itself in the form of a question. So the question number 1, I think this is the assignment question which I have just given it here, and based on what we discussed, I hope everyone should be able to answer this question. Pick up the incorrect statement among the following, not the correct, incorrect. Yes, I mean B. So any other answers apart from B? B only, B. Okay. So as everyone says, the the right answer, which is nothing but the incorrect statement, is for this question is B. So I hope everybody will know, because as we just now discussed, glassy state will be is a non-equilibrium state, whereas the rubber is a equilibrium state. And if you as I said, at the same temperature and pressure, the volume of the glassy state that you are going to obtain after cooling the polymer melt will basically depend upon its thermal history or history on how you are going to process that polymer melt to bring it to that particular state. Then the option number D, segmental flexibility, is almost non-existent. Yes, because in the glassy state the polymers will be frozen. They will be typically more in a locked or arrested state. So segmental flexibility is non-existent. At the same time, if you go for a rubbery state, the due to the thermal energy that these molecules possess, the segmental mobility will be more. So the segmental mobility exists in case of the rubbery state. Glassy state, since it's a non-equilibrated state, you cannot use equation of state to you cannot use the equation of the state to determine its properties. Well, this is about the discussion that again, so this relaxation process, I mean everything over here typically goes to that relaxation process. This relaxation process can happen at many levels. So we discussed about relaxation, but this relaxation happens starting from uh, the CC bond rotation, starting from the relaxation of your side groups to the segments to the overall macromolecular chain. So each at every level there is a relaxation. Of course, it will be slow or fast depending upon the what do you say, depending upon the bond that you're considering. Let's say, for example, if it is a CC bond rotation, then that will be typically more fast compared to the relaxation of the overall macromolecular chain, which is going to be a slow process because the polymer chains will be entangled to each other. So due to that, it will be more of a slow process. So this ends the discussion on the glass transition here. So again, there are lots of other ways to we did not discuss about the ways to determine the glass transition temperature. So one of the ways is the differential scanning calorimetry, so that we saw in the last session. And apart from that, there are also other standardized tests, and I encourage all of you to actually go and look at them and see how the glass transition temperature is usually determined and what kind of tests exist, and how they are being conducted, and more importantly their working principle behind each of this characterization technique to determine the glass transition temperature of several polymers. There are multiple different ways. So one is your differential scanning calorimetry, another one is called DMA, dynamic mechanical analyzer, and another one you have something called as an AC chip calorimetry. So there are lot of different techniques to accurately determine the glass transition temperature. Even in DSC itself you have two different types of DSC. So glass transition is itself an area of research most widely, I mean, in the polymer, the people who work on polymer chemistry, as well as polymer physics, they do a lot of research work on understanding about this glass transition temperature. Because if you just Google out, you can see even you can see lots of papers on how to modulate this glass transition temperature or understanding the fundamentals of glass transition temperature. It's still a widely explored research topic in polymer science. So if you are interested, you're always welcome to read all, the papers and then try to understand how this, and you will be able to appreciate about this about the importance of glass transition temperature in polymer sciences. So going to the second one, the next topic is basically the copolymer. So this is typically what we also discussed in the week 2 session, where we discussed about what is a copolymer? How is it different from a homopolymer? So copolymers will have one or more than one monomeric units in its structure. Depending upon the arrangement of the monomers, you can actually categorize them as, some of the examples are alternating copolymer, random copolymer, then after that you have block copolymers, graph polymers, then periodic copolymers, aperiodic copolymers. So these are all these classifications of polymers or of copolymers are only based on the way these two monomers are arranged in the polymer structure. So there are certain things called reactivity ratios. I hope everybody will be having an idea of what is reactivity ratio. Just a very, can anyone tell me roughly what is this reactivity ratio is? R. If you have two monomers and then they are going to, let's say, two different monomers, and then if they are going to um, interact with each other and then form a copolymer or form a bond with each other and form a copolymer, this reactivity ratio is going to be something of importance, because we need to know when you add two monomers whether they are compatible with each other or whether they can react to form a copolymer. First thing is that. Second thing, what kind of copolymers will be formed? Since we discussed about different types of copolymers like alternating, random, block, so depending upon this reactivity ratio, you can actually control the, what do you say? You can actually control the type of polymer that's get synthesized from your monomer. So R is nothing but reactivity ratio, and this determines the type of polymer you get, type of polymers synthesized. So you will have two different reactivity ratios for a copolymer, which is one is R1 and another one is R2. So depending upon the values of R1 and R2 or RA and RB, you can determine whether a particular polymer will be a copolymer, I mean whether it will be an alternating copolymer or a random copolymer or a block copolymer. Suppose, let's say for example, if both of these values were, I mean, what will be the expression for this R1 and R2? It's there in the lecture slides. So please go through those, this because you cannot really, as I said previously also, it is not possible for every one of us to remember whether a particular, if I give you a polymer or let's say a copolymer, we should be able to tell whether it's a random or a block copolymer. If given the data, then we should be able to judge, or this will be typically something, it will be important, because if you are taking two monomers, it completely depends upon you how to manipulate the synthesis condition so that you can get a type of copolymer that you want, so that it can be useful for certain applications. So block copolymers can be suitable for certain application, alternating copolymers can be suitable for some other applications. So you can actually play around with the synthesis condition and then try to change this reactivity ratio between the two monomers so that you can get the desired product as you want. So this is going to be of some importance. So please have a look at it in the lecture and see how does the values of R really affect what kind of polymers you are going to generate out of that. This is about the reactivity ratio. So next what we are going to do is we are going to go for some problems. So before that, if you have anything, you can ask me right now, or you guys can take let's take a 1 or 2 minute I mean let's take a 3 minute to 5 minutes break before we start our next session. It's up to you. So yeah. So let's resume our session by 6:13. 6:13, yeah, 6:13 would be fine. I guess 3 minutes, 3 to 5 minutes, 6:13 to 6:15. We will start our session. So, shall we start or shall we just wait for another minute or so and then we can begin? Anyway, I'll just give the question, so let it be there for display. This we discussed in the last class. Of course, we didn't solve. So let's start with this question before we begin the questions for this session. So we are accumulating few questions. So let's try to solve them as in when we as we go through the course. So this was discussed in the last class, as I said. There are two different PTFE specimen. The PTFE1 has a density of 2.14 gram per cc. Crystallinity is 50 percentage. And the PTFE2 specimen has a density of 2.215 gram per cc. Crystallinity is 75 percentage. Now assume that the polymers are pure and defect free and find the density of the 100% amorphous specimen. Well, this was supposed to be something that I gave it like kind of a thing to do it during the week. But in case if any one of you were not available for the last class, then you are welcome to solve this right now. You have the density of the overall PTFE system, PTFE1, and you have the crystallinity, which is your XC, that value is there. You do not have row crystal and row amorphous. Like that, for two different system you have row overall and crystallinity, but row crystal and row amorphous is not given, but you have two equations and two unknowns. So you can solve that equation and then you can get the density for crystals phase as well as amorphous phase, or crystal domain or an amorphous domain. So how to go about this question? This you can put it for PTFE1, the first system, and this can be for your second system. You just need to substitute two equations, two unknowns, so you should be able to get the value for row crystal and row amorphous. Of course, the question says only to give the density of pure 100% amorphous specimen, but once you calculate for amorphous calculating the density for the crystal domain should not be a difficult task. So that's the reason I am demanding for row crystal as well as row amorphous value. So let's start solving. So just plug in those values from the question. Row overall is 2.144. Row crystal, let it be as row crystal, times crystallinity is 50 percentage, so I'm going to take it here as 0.5. Of course, it should be taken in fractions. and this is rho amorphous, so let me take it as rho amorphous, which is not known to us, which we are supposed to calculate, times 1 minus zero point 0.5, so which is going to be 0.5. So this is one equation. Let me mark this as equation 1. Similarly, you have to write the equation 2. So that is 2.215 is nothing but rho crystal, but this time around the crystallinity percentage is different, 75 percentage, so that is in terms of fraction it is 0.75 plus rho amorphous times 1 minus 0.75, so I am going to write it as directly as 0.25. So two equations, and let me mark this as equation 2. So two equations, two unknowns, what is the value of rho crystal or rho amorphous? I guess this is basic arithmetics now. Yes, anyone? So please calculate the values. I am also going to do the calculation. Oh, is my calculations correct? I think this should be 2.286, I believe. 2.286 gram per cc. So if rho crystal is this, then rho amorphous will be nothing but rho amorphous will be 2.002 gram per cc. Is this correct? Gram per cc. So rho crystal is going to be 2.286 gram per cc and rho amorphous is going to be 2.002 gram per cc, or you can say 2 gram per cc. So this is the way you calculate the density of pure 100% amorphous specimen. So if you have got this answer, then it's well and good, or if you have any other answers, please let me know before we move to the next question. Nothing to, I mean, is the answer matching? So let's see this question. In case if you have anything to ask for that question, then please let me know. Otherwise, let's start with this question. The Tg of homopolymers A and B are plus 100 degrees Celsius and minus 70 degrees Celsius respectively. We are supposed to calculate the Tg, that is your glass transition temperature, of a random copolymer of A and B having 40 weight percentage A and 60 weight percentage B. How to calculate this Tg? Can we take the Tg as a simple additive of I mean the Tg of a random copolymer as a simple additive of the Tg of a homopolymers A and B? Yes, no, any idea? Can I write it this way? Is this fine? I mean, so if it is not correct, then please let me know. Weight percentage of A in terms of fraction is zero point 0.4. So that times plus 100 plus weight percentage of B is 60 percentage. So zero point 0.6 times minus 70. So Tg of copolymer is nothing but 40 minus 42. So that is minus 2 degrees Celsius. Is this fine? some other value formula may be different. Any? So this is how you calculate the Tg of a random copolymer. Of course, in case of blends, the formula will be different. That we will discuss in the next class. But in case of a copolymer, you can take them as a simple additive of the homopolymers A and B, and then you can use this relationship to calculate their Tg. So by varying the weight percentage, as I said previously, you can really manipulate, or yeah, you can say manipulate the Tg of the copolymer that you want, or that you want to synthesize. So it is up to us to vary the ratio as per our wish, so that we can generate the polymer that we want for our desired application. It's not just about the type of polymer that we want to generate, but also we can have a we can have a we can also try to control the Tg of the material that we want for a particular application. So you can also it will be a very good task. You can also go and look at different kinds of polymers, and what kind of Tg they have, like what are the values of their glass transition temperature, and where are they typically applied. So a polymer, its glass transition temperature, and where are they applied, and you can try to correlate whether this glass transition temperature basically is a responsible factor for their application in a particular field or in a particular application. So that will be a good task where you can actually see how varying this glass transition temperature will significantly change where the particular polymer can be used. So going to the next question. So the next question is, a linear amorphous polymer has a Tg of 10 degrees Celsius. At 28 degrees Celsius, it has a viscosity of 4 times 10 to the power 8 poise, which is the unit of viscosity. We are asked to calculate the viscosity of the polymer at its Tg. So we have something, we have a particular viscosity value at a particular temperature, for a particular temperature. Now we know the value of Tg, but they are asking us to calculate what will be the viscosity at this Tg. Similarly, the question can also be like this. They can give you the value of the viscosity of the polymer at Tg, and then ask you to calculate the viscosity of the polymer at at a different temperature. Or the question could also be like this, wherein they give you the viscosity at Tg and the viscosity at a particular temperature, and what temperature you are going to measure that, and then ask you to calculate the value of Tb. So all sorts of permutation combinations are possible with respect to this question. You can be asked to calculate the viscosity at Tg or at any particular temperature, or you can be given the viscosity values and be asked to calculate at what temperature this viscosity can at what temperature the polymer can exhibit this viscosity, or what is the glass transition temperature for the particular polymer based on that data given to us. So how do you approach this problem? Think over it for some time, because you are supposed to use some sort of equation. It's not going to be a direct linear relationship, unlike what we saw in the last two examples. This is going to be a empirical relationship. So but have a thought over it, and then let's discuss it. So we saw something about so called as a WLF equation, right? William Landau Ferry equation. So you have to apply that here to get the value of the viscosity of the polymer at its Tg. What is the equation? Any idea? I mean, it's they. If you go through the, if you have been through the course, then it is there in the course. I mean, I think week. Sorry, the fourth lecture for this week, fourth or fifth lecture for this week. In week 4, I think fourth or the fifth lecture. So over there we have discussed about WLF equation, shift factors. I'll just give that equation. So it is ln eta by eta at glass transition temperature equals to minus C1, okay, T minus glass transition temperature divided by T minus Tg minus C2. Here the value of C1 and C2 are 17.44 and 51.6 respectively. So these are the universal constant values. So this is the empirical relationship, and C1 and C2 are the empirical are the universal constants. So based on this, you just need to now plug in these values and calculate the viscosity at its glass transition temperature, or at the glass transition temperature of the polymer. So that will be nothing but ln ln of eta is 4 times 10 to the power 8 divided by eta g, that is equal to minus of 17.44. Your T is 28 degrees Celsius. I am going to take here everything in terms of Kelvin. So, or you can also take it in terms of Celsius, because it's anyway going to be the difference. So that will be almost the same. So 18 by 28 minus Tg, which is 10, minus 51.6. Now you just need to calculate the value. So let's calculate ln of 4 times 10 to the power 8 by eta g is equal to minus of 17.44 times 18. 313.92. So 10 minus 51.6 minus 41.6. So it is 28 plus 41.6. So this is going to be this 313.92 by 60 69.6. So if you divide this 313.92 by 69.6 is 4.5103. So let me take it as 4.51. So negative of 4.51. Now we are supposed to take exponent of it. This, so 4 times 10 to the power 8 is equal to, or by eta g is exponential of minus 4.51. Point 0.01099. So I'm going to take it as point 0.011. So that will be 4 times 10 to the power 8 by point 0.11, sorry, 0.011 equals to eta g. 4 by 0.011, 363.33 times 10 to the power 8. Okay. Is everything correct? The calculations? So the viscosity of the polymer at its Tg is 363.33 times 10 to the power 8 unit is poise. So this is the viscosity of the polymer at its Tg, and it makes sense because as you see, viscosity of the polymer at its Tg is 363.33 times 10 to the power 8, and when you increase the temperature, the viscosity is reducing to 4 times 10 to the power 8. So it is again a quantitative confirmation for us that as the temperature increases, the viscosity is going to decrease, so the polymer is going to behave more like a fluid. I hope there is no doubt, but if you have anything which you are not able to understand, then please let me know so that we can go through this problem once again. Or we will take one more question, the last question for this session, before we wind up for today or for this week. Okay, if then let's proceed for the next question. So, hmm. So this was a question which was supposed to be solved last week, but was actually given as a kind of a problem which you can solve during the week. So let's see this question for today. A polymer weighing zero point 0.2 gram is dissolved in 100 ml of benzene with a relative viscosity of 1.5. The polymer obeys Mark-Houwink equation with a value of A equals 0.5 and K as 0.001. The molecular weight of the polymer is something which we are supposed to calculate. So as we saw last week itself, there are different type of viscosity. So here what we have is something called as a relative viscosity. So from this relative viscosity, you are supposed to calculate your intrinsic viscosity to find out the molecular weight of the polymer. So anyone with the answers, or shall I give this also as a okay? So let's go for some other question, but please solve this during this week. Let's take up some other new question. This will be pretty interesting. That is similar to a very routine way of solving. Question number 8, you have to do some modification to the equations that you have. You have given a polyethylene sample, you are given a polyethylene sample with the specific volume of V with a specific volume 1.042 times 10 to the power minus 3 meter cube per kg. Uh, the specific volume of the crystalline fraction and the amorphous region is given, and they are asking you to calculate the percentage crystallinity. So you are given a polyethylene sample with a specific volume of 1.042 times 10 to the power minus 3 meter cube per kg. This particular polymer shows a specific volume for the crystalline fraction as 0.989 times 10 to the power minus 3 kg, 10 to the power minus 3 meter cube per kg specific volume, and the amorphous fraction shows a specific volume of about 1.160 times 10 to the power minus 3 meters cube per kg. Based on this data, you are supposed to calculate the percentage of crystallinity. So here you are not given the density, but you are given the specific volume. So you are just supposed to modify this equation that we saw here based on specific volume, and then it just, once you convert that equation, it's just a simple substitution again, mathematics. But what will be the equation? So I'll just copy paste this. You're just supposed to modify this equation based on or as per the specific volume. Once you are done with that, then it's just, as I said, it's good to go. You're going to just do plug and play with the values, numerical values. So how can you relate density and specific volume? Yes, I'm not saying here volume, here it's a specific volume. So you can look at the units and then try to guess. So density is mass per volume, mass per unit volume. So what will be the units of density? Or in terms of kg and meter? And here's, so specific volume is inversely is nothing but what he says, inversely proportional to density. So rho density is nothing but 1 upon specific volume. So if you know this, then how will the equation now change? Can we write, like this, 1 by overall, or 1 by v uh, overall is nothing but it's equal to crystallinity xc by vc, which is nothing but your specific volume of the crystalline fraction, plus 1 minus xc divided by specific volume of your amorphous fraction. So now you just need to plug in the values. So since everywhere there is a 10 power 3 term common, I'm going to just remove all of them from the equation. So it's going to be 1 by 1.042 equals to crystallinity fraction divided by 0.989 plus 1 minus x. 1 minus this crystallinity fraction oh, by 1.160. So what will be 1 by 1.042? 0.959. This is nothing but it's equal to, well, now it's your wish, you can take it 1 by 0.989, 1.011. 0.862. So what it would be, so 0.959 minus 0.862 is equal to 1.011 minus 0.862 times the crystallinity fraction. So this is going to be point, um what, let me just calculate using calculator. It's 0.959 minus 0.862, 0.097 is equal to 0.149. 0.651, or you can say that as crystallinity is nothing but 65.1 percentage. So once you know the value of crystallinity, the amorphous percentage or the fraction of the amorphous domain within the material is going to be 34.9 percentage. Yeah. So this is the value of crystallinity or the fraction of crystalline regions present in this particular polyethylene sample, and the amorphous percentage of amorphous domains present in this particular polyethylene samples. So here it's just that only one thing, you should know what is the meaning of specific volume and how it is related to the density. So once given this equation, you are just supposed to substitute the, I mean, you are just going to substitute and get the value. So additional thing, whenever you have specific before any of the variable, it means that that particular variable divided by mass. So specific volume is nothing but volume divided by the mass of the material or the system, volume of the system by mass of the system. So this is consistent throughout any variables that you take or anything that has a word specific before that particular variable. So you can take this as a thumb rule, or you can remember this, that whenever you have specific before any variable, then it means that that particular variable divided by the mass of the system that you are taking into consideration. So let's conclude our session for today here, because we are about to cross our 2 hour schedule. So if you have any doubts, you're welcome to ask me right now, or otherwise we'll conclude our session for today. Oh, it's there in the slides itself. I have updated the slides so you can actually, if you check the presentation folders throughout this weekly sheet, then you'll be able to find out my email ID. Okay. Okay, so then let me conclude the session. So I thank everyone for joining today's session. Our next session will be on 24th August from 5 p.m. to 7 p.m. for week 5 live interaction session. So I thank Professor Abhijit Deshpande sir and the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon. So I hope everybody has a great weekend ahead and have a great week ahead as well. So thank you and bye. Thank you.